Okay, now let's proceed and try to motivate our discussion by proving that Q does not satisfy the property that every bounded from above set has a least upper bound. And so this is why we need to construct the real numbers if we want to have that property. Okay, so let's look at the set. So let's define the set A to be equal to the set of rational numbers, so all the r's in Q such that r squared is less than 2. Then we will show that this set does not have a least upper bound in Q. I don't know if I can Q. Okay. Let's see why this is the case. But first, we'll need to remind ourselves of some basic property of the function r squared, x squared. So, is increasing over the positive real numbers, or the positive rational numbers. It's actually increasing over the sort of non-negative rational numbers. But this will not be of interest to us. So let's show that this function is increasing. Indeed, if x is less than y, where both x and y are in Q, we have that also x times x is less than x times y. This is a property of the rational numbers. And if you multiply two non-negative numbers, is non-negative. And remember that by assumption, we're just considering f to be defined over the positive rational numbers. So then this property here tells you that x squared is less than x times y, but at the same time, if you just look at where you already know that x is less than y, so if you multiply the inequality up here by y instead of by x, you get that this is less than y squared. And so this implies that x squared is less than y squared, and this is f of y. All this is f of x. So starting from the assumption that x is less than y, we arrive at the conclusion that f of x is less than f of y. And this is exactly what it means for a function to be increasing. Okay, so now let's prove. Let's go back. To showing that A is bounded but it does not have a least upper bound in Q. So claim 1, A is bounded to see this, we show that 2 is an upper bound. Well, if R belongs to A, then R squared is less than 2, which is in turn less than 2 squared. And yeah, this is equal to 4, right? And this implies that R squared minus 4 is less than 0. So now we check that this, well, this is exactly equal to R minus 2 times R plus 2. So this product is less than 0. So there are two possibilities here. So if R is negative, then it is clearly less than 2. If R is greater than 0, then R plus 2 is greater than 0. And so we may multiply this expression here by 1 over R plus 2, which is well defined because R plus 2 is not equal to 0. And this proves that R minus 2 is less than 0, which is the same as saying that R is less than 2. Okay, so we picked any element in A and we show that that element is less than 2. So 2 is an upper bound. And 2 belongs to the rational numbers, of course. We have let's construct an upper bound for A.